Hello again. Let's revisit things from the last video. There was more stuff I could have inserted at the time, but I didn't want to overwhelm you. I'm going to introduce two new definitions. I'm going to keep my old stuff the way it was. Now remember last time we defined dx and dy? And notice that dy is your approximation to f of p minus f of c. Now it would be nice to actually have someone that directly equaled f of p minus f of c. And that guy, by the way, we're going to denote him now. That's delta y. Now what we're going to do is we're going to let delta, that's not delta dx, sorry guys, that's just delta x. We're going to let delta x spot on equal dx. But now delta y is not going to directly equal dy, though it will approximately equal dy. Delta y, though, is exactly equal to f of p, which is this guy right here, because if you add c plus delta x, you'll get p. Remember, guys, dx is p minus c, and if you add p minus c to c, you'll get p. So c plus delta x hence equals p. Likewise, c, because they're equal, c plus dx equals p. So c plus delta x, that's p, so that's f of p minus f of c. That's delta y. Now dy is our approximation. Well, no, actually, let me back up. dy is our differential. It's approximately equal to delta y. Our local linear approximation, that's this guy right here. That's f of c plus dy. dy is our differential. Our local linear approximation, again, is it's not f of p. F of p is our exact value. But our tangent line approximation, or linear approximation, I should say, is f of c plus f prime of c p minus c. Again, that's our linear approximation or tangent line approximation. It's this guy plus this guy. If I said the word local, I shouldn't have. Throw that out. I don't know why that's going through my head. Now, this is our delta y. That's our differential with y. And it's approximately, but not exactly equal to... This is our dy. Excuse me. This is our dy, which is our... This is dy. This guy right here. That's dy. This guy right here is dy, not delta y. But... Now, delta y, on the other hand, is the exact value of p minus f of c, whereas dy is this guy right here. So if I got tongue-tied earlier, dy is this guy right here, f prime c p minus c. That's dy. Whereas delta y is f p minus f of c, which is this guy right here, f of c plus delta x quantity minus f of c. That's delta y, okay? So, here's our dy. Whereas here's our delta y. So contrast dy and delta y. Now, delta x and dx are the same thing. There's nothing to do, okay? So delta y is the exact difference between f of p and f of c. In general, that's hard to find. And what we're going to do in general is just be satisfied with dy. Now, dy is going to be a little off. It won't be perfect, but it'll usually be really good. Delta y is the exact thing, and it's perfect, but it may be very hard to find, and the reason is because f of p right here itself is hard to find. If you can't find f of p very well, it's going to be, there's no way you can really find delta y. Even if you do know it, f of c is easy, but f of p is hard in general, and hence delta y in general will be hard, okay? Now, again, we had this example. We did... P was 64.12. We let f of x equal x to the 2/3. We did our f prime, and we got, throw 64 into f, we got 16. Throw 64 into f prime from the last video, we got 1/6. That's all well and good. And then we got an approximation for f of 64.12, which is 64.12 to the 2/3 power. So we use this much easier guy right here, this approximation, and we came up with 16.02, and we recall that dy is 0.02, whereas dx is 0.12, where dx really comes first. So dx is 0.12, dy is 0.02. Now, but notice, guys, I didn't give you, if asked for it, dx would equal, delta x is, delta x, there's nothing more to do. That's just going to be 0.12 as well. Delta x and dx are the same. So there's no big deal there. So So delta x is spot on equal to 0.12. Now, whereas, now delta y, not dy, but delta y is equal to 0.0199. Let's see, we got 1, 2, 3, 4 nines and a 376, and then so on forever. It really, delta y, there's no way to really represent delta y. You would have to write forever. It goes on forever. It's an irrational number. So delta y is that. Because remember, guys, to get delta y, you do f of p, the exact f of p, which you have to use a calculator to get. That's the hard part. That's that guy right there. Minus f of c, which is just 16. The f of c is 64. So you do 16.01 blah, 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 minus 16, and you get the 0.019999376, so on, whatever. So that's your delta y. Now keep in mind, now guys, dy is 0.02, whereas delta y is this irrational number. But notice they're mighty close. Dy is very pretty, delta y not so much. But delta y, you know, is even more honest, but it's in general hard to find. Delta y is how much, that's the difference between f of p and f of c, the exact difference. Like f of 16.12 minus f of 64, that is exactly delta y. Now dy is just an approximation to that, but it's a very good approximation, although not perfect, very good. Delta y is in theory perfect. You know, delta y is perfect, but that's a hard guy to find. Dy is usually much easier to find. And notice they're close. They're not exact, they're not identical, but they're close. So there's that. So delta y is f of p minus f of c. Here is your f of p, and way up here from the almost early on is your f of c. Okay, and subtract the 2 and you'll get delta y. Now dy, remember from the last video we went through this. We did a little bit of calculus, easy calculus though, and we got that 16.02. That was from the last video that we got our dy. And we also got our tangent line approximation. That 16.02, remember 16.02 is not exactly f of 64.12, but it's mighty close. 16.02 is mighty close to being 64.12 raised to the power of 2/3. It's mighty close to being that. It's not identical, but it's mighty close to equaling that. So there's that. Now, this guy right here is the exact value. The 16.01999 whatever, that really, this whole thing here, this irrational number really is 64.12 raised to the power of entity 2/3. Well, but in general, that's hard to find. You know, what if you don't have a calculator? What if you're taking a test and your professor won't let you have one? Well, you know, you'll want to do this, okay? So again, this is the whole business about delta x and delta y. Okay, I could have done that on these past few examples or whatever. I just didn't want to I didn't want to overwhelm you on the last video. And up here again, well, we define, remember delta x is dx, whereas delta y is fp minus fc. Okay, f of p minus f of c, I should say. Okay. So there's that, and again, back when I did this example here, the square root of 25.22. Now delta y would be, it wouldn't be 0.022 exactly. Delta y, now dy really is 0.022. Delta y would be, well, let's see. Delta y would just be this guy right here that goes on forever without the 5. Remember, you got to subtract off the 20. You got to subtract off the 5 to get what you're after. Okay. And let me just copy and paste the decimal portion without the 5. Just the 0.02 part. Yeah, that's it. So delta y would be 0.0219, so on forever. You'd have to write forever. It's an irrational number. But dy is much prettier. Dy is not exact, but it's much nicer to find. Delta y is exact, but could be very hard to find. And remember, our tangent, the 5 the 5.021, no, excuse me, back up. The 5.022, that is our tangent line approximation. Okay, remember from the last example, 16.02, this was our, if I said it wrong a minute ago, forgive me, I think I said it right, I'm pretty sure I said it correctly. 16.02 is our tangent line approximation. This guy down here is not an approximation, he's our real McCoy. The 16.02 is our tangent line approximation. So if I said that wrong a minute ago, forgive me. So 16.02 is my tangent line approximation, whereas this is the exact McCoy. So, and I said it down here. So yeah, indeed, there it is. 16.02 is our tangent line approximation. So there's that. And then in a similar vein down here, this is the real McCoy, but in general hard to find. This right here is still very good, not exact, but this is the tangent line approximation right here. It's still quite good. And here's delta y. Now here's dx. Now delta x and dx are the same, so delta x is obviously equal to 0.22. Okay, and if you want me to write it just for completion, I will. Oh well. But so delta x is of course equal to 0.20. There's no thinking there. It's just delta x and dx are always the same. Okay, so there's that. So that's just the whole business about delta x and delta x and delta y. They're the or delta y anyway. It's the perfect world difference. It's the difference. If we had all the resources in the universe, we could just find delta y all the time and not even worry about dy. But we don't, and dy is very handy. Delta y can be a real pain. Delta y can be a real pain. Dy is handy. Okay. Even though dy is not exactly right in general. Okay. There may be a real pretty problem. I'm not sure, but anyway. Moving on. Consider the tangent of 134 degrees. Guys, that's the tangent of pi times 134 over 180. So we're going to let f of x equal the tan of pi x over 180. I want to stay in degrees. I can do that, but I have to insert a correction factor of pi over 180. So, and we're going to let c be 135. Notice that 134 is close to something that's trigonometric in degrees is close to 135. Well, 135 is a pretty trigonometric number, right? That's an angle where you can do some nice things with sine and cosine and all that. Let's see, 135 would put us in quadrant 2. The tangent, if you just throw 135 in here, that you're just finding the tangent of 135 degrees. The tangent of 135 degrees is -1 by trigonometry. But anyway, now the tangent of 134 is hard. That's not a very pretty number to find. It's no doubt irrational. I'm quite certain that's irrational. So, but we're going to let y equal secant squared of x in radians, where x is in radians. And we're naturally going to let c be 135 and p be 134. And then we just go to town. Of course, now p minus c is -1 this time, because c is 135, whereas p is just 134. So we get, now the tangent of p is approximately equal to, well, again, this is just 135 degrees. Guys, what I did here is this is 135 times pi over 180. But what I'm doing is 135 over 180, that reduces to 3/4, okay? So you can turn the 3 back into 135 and the 4 back into 180 if you want to unreduce the fraction, so to speak. But anyway, this is just the tangent of 135 degrees, which is -1. And the -1 minus pi over 180 times... Now, guys, remember, you got to do the derivative of the tangent, which is the secant squared. So you do the pi over 180 and then times... Now, guys, how did we get pi over 180? I owe you a little bit of explanation there. You know what? Yeah, I do owe you explanation. Sorry about that. Yeah, that's terrible. My bad, guys. So let me put... I need to differentiate f of x, don't I? Then f prime of x, and I didn't even do it right anyway. We use the chain rule. So it's just... So if f of x is tan of this, so f prime of x, we do the chain rule. If you derivate the tan part, you just get the secant squared. And then that's my 180s down there. But then by the chain rule, guys, remember, this is the secant squared of u, and then you got to derivate, u is this fraction inside here, remember, and if you derivate u, this guy with respect to x inside here, this is du by dx. Wait, no, this is u, but if we do du by dx, that's just going to give me pi over 180. So, and we can stick that in front by commutativity. It's kind of messy to stick it to the right. It's okay to do that, but it's kind of messy. So there's, by the chain rule, we get that pi over 180 there, okay, guys? And so there's that. And I'm sorry I put the cart in front of the horse. I needed to do this first. So again, c is 135, p is 134. So p minus c is neg 1. And then by the tangent line approximation, I do the tangent of c. And again, guys, what I do is I throw one, c is 135. I throw 135 right here. I get 135 pi over 180, but that 135 over 180, you can reduce the fraction. You need to get used to doing that anyway. And you divide both of them by 45, and you'll get 3/4. 45 goes into 135 4 times. 45 goes into 180 4 times. So you get 3/4. So it's 3 pi over 4 when you throw 135 into x right here, okay? So you get the tangent of 3 pi over 4. So when we throw in our c equals 135 and we reduce and we get this. And then, now that negative 1, guys, p minus c is neg 1, so I just go ahead and take it out as a negative. What we're going to do, really, this is a plus sign here. It started at, well, it's not a plus sign anymore. It started out as a plus sign, and we had pi over 180, and we had times the secant squared. By the chain rule, we had the pi over 180, we had the secant squared, and we have negative 1 over here. But we have to, don't forget your p minus c that has to go here. But p minus c is neg 1. And if skipping that step bothers you, what I did was, what I really had, I had a negative 1 multiplying everything. I had a negative 1 over here. You could really put it, by commutativity, you can move that neg 1 all the way over here. See, this is the p minus c, okay? So you got to have that p minus c term. And then, but I just took that negative 1 and brought him all the way up here to the front, and I took him out on this plus sign here. So this negative 1 we can get rid of again, and I'm going to go back to where I came from and turn that plus sign back into a minus sign like that, okay? And then you just do, now the secant squared of 3/4, that's going to be positive 2, but that positive 2 is going to bump into that negative sign. You just get minus 2 times pi over 180, so we have negative 1 minus 2 times pi over 180. And then, now that reduces to, now that's negative 1 minus pi over 90, because that 2 and 180 reduces to 1/90th. Okay, and then that's about equal to negative 1.035530314. And that's not bad, since the tangent of 134 degrees was this guy right here. It's pretty close. It's not too bad. That's a decent approximation. As long as it's not something that demands too much precision, we're pretty close. It's not as good as some of those previous ones, but it's not too bad. Now, guys, the negative 1, in a way, this time, I know what you're going to say. Well, Jason, was this really any easier than just, well, what you can do is you can approximate pi with roughly, in general, your professor will want you to round. He'll probably, he or she or he will want you to go, she'll probably want you to go out, it depends, 3 or 4 places, maybe 5 or 6. That depends on their style. But you can just do this by hand. You can approximate and round pi. You can treat pi like it's roughly equal, not exactly, but roughly equal to 3.14, and then something. But anyway, I did this. This wasn't really very pretty either. But I did it to just show you the process. In a way, this didn't turn out pretty like I'd hoped, but it turned out correct. And pi is roughly equal to 3.14159, and then more and more, so on. It keeps on going and going. But anyway, guys, I'm out of time. I'll stop the video here. See you on the next video. Bye-bye.